me to attend this meeting. I don't know how much time I have, but and this doesn't work. Oh, it does. So let me start. I wrote down here a list of what I call tough challenges. And not surprising, the first one is about the collection and management of big data. POS stands for Production of Official Statistics. I should say I attended yesterday a very interesting workshop on big data, and there will be an obvious overlap between what I'm going to say about it and what has been said already yesterday. So I'm here mostly for those who couldn't attend the workshop yesterday, but maybe I shall highlight some other aspects. Integration of computer science for production of official statistics from big data, data accessibility, privacy and confidentiality, possible use of internet panels, how to deal with mode effects, future censuses and small area estimation, integration of statistics and geospatial information. And I also like to talk a little bit about this question: are universities preparing students to work at national statistical offices? Now, I know there's no way I will be able to cover all of those topics, so I'll just see how we go about them. Let me start, just as a warm-up for this big data business, with a very simple, but I think quite fundamental example: count of the number of vehicles crossing road sections. This is how it's done in Israel, and I'm sure in many other countries. You have to basically put a rubber tube across the road, and every time that a car crosses over there, it sends a pulse, which is here in the, how does this work? Here on the right-hand side, and this way you count the number of vehicles. It's also, I should say, very risky because you have to put this tube while traffic is actually running. So the question is, in our modern days, why not get this information and much more from cell phone companies, available in principle for each time point? And by the way, I'm told the cell phones don't even have to be on in order to send those signals. Yesterday in the workshop, they gave some examples from Mexico and Holland where they already do this, although I think they use traffic sensors rather than phone. Another famous example is what's known as the BPP, Billion Price Project, based on 5 million commodities sold online to predict the current price index. I remind you, to compute the current price index, you actually need to have two quite costly surveys: a family expenditure survey to estimate the weights, and then also send people to stores, etc., to collect information about the prices. I'll get back to this later. So, as I look at it, big data, big problems, big headache. Is the issue of coverage selection bias. Again, I'm only talking about production of official statistics now. Data accessibility. You need new legislation. Privacy, data protection. Disclosure control. Computer storage. Linkage, integration of different files. There is also a risk of data manipulation, but I won't talk about that. We have two types of big data. Type 1, which is data contained from sensors, cameras, cell phones, is generally structured and accurate. But then we have the type 2, data obtained from social networks, e-commerce, etc., generally diverse, unstructured, and also appears irregularly. Type 1 measurements are available continuously, very high frequency. Should POS publication be mostly in the form of graphs and pictures? I think there is also a session about it later. If aggregate data are still needed, how should the big data be transformed to, say, monthly aggregates? By sampling? Will random sampling continue playing an important role when processing big data? Coverage bias, a major concern in the use of big data. Big data of credit card transactions contains no information on transactions made with other means of payments. Opinion expressed in social networks are different from opinion held by the general public. I think this is important. No bias should occur when using big data to predict other variables estimated from standard surveys. For example, use the BPP to predict the CPI. I know this has been done in the US. Use job advertisements to predict employment. Use satellite images to predict crops. It requires proper statistical analysis to identify and test routinely the prediction models. Big data are supposedly free of sampling errors, as long as you don't sample. Are measures of error still an issue? What? Which kind? Measure of bias? How? By comparing to traditional estimates? One may ask, in this case, why do we need the big data if we're going to correct them based on the traditional surveys? I know the answer. I want measurement errors, other type of errors. Big data for subpopulations. In national statistical offices, we publish estimates for subpopulations as defined by age, gender, ethnicity, geography. Big data may not contain all this information. So it will require massive linkage if missing information is available in other big files. So will traditional sample surveys always be needed? I remind you, my role is just to tell you what the challenges are, not how to deal with them. We are familiar with design-based estimators, model-based estimators, model-assisted estimators. Here is something new that comes up, which I think is referred to as algorithmic estimators. What are those? Those are the result of computational algorithms applied to the raw big data. I'm writing a paper on all this. I'm almost done. So I give an example there of measure of religiosity. I hope I pronounced it correctly. Let me talk a little bit about computer engineering for production of official statistics from big data. We're no longer talking about gigabytes. Terabytes, petabytes are the new standards. Computing facilities at most, if not all, national statistical offices cannot store and handle such high volumes of data, definitely not in Israel. So the possible obvious solution, use the cloud storage, management, and processing facilities. But here is the big problem: data protection. Multiple users, data distributed over a large number of devices. So here is the possible solution, and I know that in several places they're working on it, what can be called as the private cloud installation, incorporating all the local computers, combined management of storage space and processing power of the separate service. I'm told that the new PCs are going to have about 1 terabyte of storage space. This means that if you have 1,000 of those, you have basically 1,000 terabyte. This is a lot. Something about privacy. There are two aspects to it. The first one is just to protect the data from intruders. This is very expensive. I can tell you in Israel they require us now to put new devices which amount to about 15% of our annual budget. But I won't talk about it. Now we come to statistical disclosure control. guarantee that the data released cannot be used to reveal private confidential data. And my point is that current SDC procedures need extensive modifications. Here are just simple examples. One way to achieve statistical disclosure control is by releasing synthetic data. Synthetic data is basically data generated from models. So are we supposed now to generate new big synthetic data? Another example is what's known as research or safe rooms or data enclaves. It's the same. Available procedures for release of data and control of output need major revision. There is a new trend, release synthetic data for researchers before they actually get the real data. But here again, if I'm supposed to release synthetic data, am I supposed to generate new big data? Okay, so some summary remarks. New expensive computing facilities, new data processing techniques, new linkage methods, new visualization methods, new analytic methods, new measures of errors. This is all what is involved. Only some of the big challenges facing computer scientists and statisticians in the use of big data for the production of official statistics. But we cannot, of course, ignore the big potential advantages: timeliness, much broader coverage, although, as I mentioned, coverage bias, no sampling frames, no questionnaires, no interviewers. Considering the constant decline in response rates in traditional surveys, use of big data, I wrote, seems inevitable, is inevitable. I read somewhere saying big data will almost always be there. I want to say big data will just grow bigger and bigger. And I want now to consider something very different. Possible use of internet panels for production of official statistics. I should say I think that my main role in this conference is to introduce some statistical expressions which used to be the main tool of statisticians, but for some reason I haven't seen even one of them until now. So I apologize that in the next few slides I will show some expressions. I'm sure some of you are actually waiting for them. Web surveys have huge advantages over traditional surveys. I don't think I have to say much about that. But the main problem, volunteers with access to the internet. So basically we get only information from those. At best, they represent a population of internet users. What is an internet panel, or I'll call it iPanel? Big group of volunteers agreeing to participate regularly in surveys, often in return to certain incentives. The iPanel is possibly recruited by probability sampling, and the samples selected from the iPanel often selected by probability sampling. So here is the big challenge. What we are really interested in is not just in internet users, but we want to get information about the general population. So estimate general population parameters from iPanel samples. Can we do that? So here are two approaches that I've seen in the literature. The one is what you may know from observational studies, propensity scores. How is it applied in this case? Select a traditional large reference sample and then treat the sample from the iPanel as the treatment sample and treat the reference sample as the control sample. And now I just do what you do in classical propensity scores. Estimate the propensity scores based on all the observations in both the treatment and the control samples. Say use logistic regression. I think this is the common procedure. Divide the treatment sample or the iPanel sample into C classes based on the estimated propensity scores. compute an adjusted weight, call it DJW, and then basically you get your estimate, say, of the finite population total. What are the assumptions around this? Or what are the problems? To begin with, it requires drawing a large reference sample, which of course can be very costly. But it also assumes those strong ignorability assumptions. If I denote by T1 for an unit, if unit I is the internet sample and 0 if it's in the reference sample, then basically what you have to assume is that T and Y are independent given covariance X that are used for the computation of the propensity scores, and there is also these other assumptions. So those conditions may hold for some, but not all the study variables of interest. There's also the question of how to estimate the variance of the estimators. Another common approach is basically use of calibration. You change the base weights to new weights such that for observed survey variable Z with known totals, you satisfy those equations, those here. Those totals might be cell totals, they might be marginal cell totals, and you may even use reliable sample estimates that you get from traditional surveys. The big advantage, it does not require a reference sample. There are some attempts actually to combine the two approaches, so combine propensity scores and calibration adjustments to basically reduce the bias even further. So what I want to do now is to propose an alternative approach. I should say right away, we haven't tried it yet, but I think it has a good potential. Denote by AI to be 1 if unit I in the population is an internet user, AI 0 otherwise. I'm assuming that every person in the population has a positive probability to have access to the internet, to be an internet user. Let Y be our study variable of interest, X be a set of covariance. So what is the distribution of Y in the population, which is FU? Just use Bayes' theorem, nothing more, and you can write it as the probability to be an internet user given X and Y times the population distribution divided by the probability to be an internet user. So what you can see from here already, if I have a model for the population distribution and I have a model for the probability to be an internet user, I can get a distribution of the internet users. Or you can switch sides of the equation. You have the observations about the internet users, so you can estimate a distribution of them. If you have a model for the probability to be an internet user, you can get the information about the population distribution. In practice, not every internet user asked to participate in the iPanel agrees. Or a person may agree but does not respond in a particular survey. So I can extend it a bit. Let Ri be 1 if internet user I is in the iPanel and responds, and Ri is 0 otherwise. So again, I know it doesn't look very appealing, I can write what is the distribution of those that respond to my iPanel sample. And you can see I have now the distribution or the probability to respond. I have the probability to be the internet user. But again, I have the distribution in the population. Once I have the estimated population in the distribution, I can estimate basically everything that I'm interested in. Here is the likelihood. I just added parameters. Inference, maximize the likelihood with respect to the unknown parameters. And then, here's what I said before. Basically, you have an estimate of the distribution in the population, and now you can estimate what you want. Here is an example. Suppose I want to estimate the population total. It's just the expected value under this distribution. In practice, no, sorry, I hit the wrong button. When the I panel selected with probabilities pi I say the I panel may be selected with probability sampling, and the covariates are unknown for units outside the I panel sample, I can just use this basically Horwitz-Thompson type estimator to get the estimator of the population total. Here are some remarks. A full parametric inference requires specifying models for the probability to be an internet user and the probability to respond. The likelihood can become complicated and maybe even face identifiability problems, but by the use of what's known as empirical likelihood, things are very much simplified. Although none of the stochastic processes in the likelihood is observable, the respondent's model is testable. And this is important using classical test statistics, because at the end of the day, I have observations from a distribution that I fitted to the data. Further simplification of the likelihood can be obtained by combining the model for the internet use and for the iPanel response into a single model, but I won't discuss this. Comparison with other approaches. Use of the proposed approach does not require the availability of a reference sample as required for the use of propensity scores and does not rely on ignorability condition. As I said before, the proposed approach requires parametric assumptions, but the model holding for the responding units can be tested, and this is important. So I'm not working in a black box. How much time do I have? Okay, I think I will skip mode effects. Maybe I just talk about the first so you know what it is all about. Different modes of responses: telephone, personal interview, mail, internet. Very often in modern surveys, we actually let the people choose which mode they want to use. The different modes sometimes offer sequentially to those who do not respond with a previous mode. What is a mode effect? It actually encompasses two confounded effects: a selection effect, differences between characteristics of sample members responding with different modes, and hence possible differences in the value of the study variables. And there is also a measurement effect of responding differently by same person depending on the mode of response. I should say there are even differences between whether someone responds with a cell phone or someone responds with a landline telephone. So again, in the next slide that I will skip, I describe what has been proposed, and then I outline another approach, but I will skip those. I want to talk about this topic: future censuses and small area estimation. Actually, my focus is on one problem in small area estimation, and I use censuses just as a motivating example. A census and small area estimation seem to define opposite concepts. A census refers to big data. Small area estimation deals with methods of estimating domain parameters based on very small or even no samples in some of the areas. As was mentioned before, modern censuses no longer door-to-door because of severe budget constraint and heavy logistic hurdles. Stephen Feinberg, in his Hansen lecture a year ago, discussed future US censuses, emphasizing the need to create exhaustive administrative record systems by linkage of multiple files. Good administrative files are the key for modern censuses. Let me describe a little bit the census in Israel, just again as a motivating example. Israel is a fairly accurate population register, almost perfect at the country level, and record linkage is relatively easy because every Israeli resident has an identity number. and there are many other individual identifiers on different files. But the population register is much less accurate for small domains, with an average enumeration error of about 13%. And the main reason for this inaccuracy at the domain level is that people moving in and out of the area often report late their change of addresses. The Israel Central Bureau of Statistics uses an integrated census, which consists of the population register corrected by estimates obtained from two coverage samples: an area sample of addresses for estimating the register undercount, and a telephone sample of people registered to the area for estimating the register overcount. So if I divide by NI the true number of people living in domain I, RI the number of people registered to domain I, PIL given R is the proportion of people living in domain I among those registered to the domain, and PIR given L the proportion of people registered to domain among those living in the domain, then you have this simple equation here, and if you just send sites, you find an estimator of the NI, which is of course your target value. So basically it's the ratio of the two proportions times the values of the number of registered. And you can easily write down what is the variance, or the approximation to the variance of your estimator. So now I can say the register for domain I improves if at least one of the proportions, PIL living among the registered or registered among the living, increases. If the two proportions sort of tend to 1, the variance goes to 0, and we can say that the census is consistent, but not consistent in its classical definition in statistics. So, small error estimation. This estimator that I just introduced is what we call a direct estimator, as it only uses data available for the domain. However, the sizes of the samples, because of budgets, etc., are very small, requiring the use of small area models, which use auxiliary information known for the data, for the area, and borrow strength across the areas. So I think many of you are familiar with this classical Fay-Harriott model. And if I go one step further, here is this classical small Fay-Harriott estimator of the area. In our case, remember, theta I is just the ratio of those two probabilities. I can skip this one. Here comes my main issue or main challenge. The use of model-dependent predictors raises the question how to define and estimate the mean square error, or the prediction mean square error of my estimator. A prediction mean square error is required for every area separately, and this is important, not just an average over all the areas. Common prediction mean square error estimators account for all model sources of error, including the variance of what is known as the random effect. My view is the prediction mean square error should generally condition on what you want to estimate, and only account for the variance over all possible sample selections. So the prediction mean square error of the number of people living in an area, here is the estimator again, should reflect the error in predicting the count Ni for a given domain at a given time, and not the error over all possible values of the true count under a model. There is one specific true count to predict. Bayesian interpretation of the random effects as reflecting prior uncertainty about the sign and magnitude of what is actually the random effects, the true value minus its predictor via the axis, is okay. But once we estimate the variance of them, we basically average over other areas. And this is not likely to be accepted by an officer from a given area. And users are used to design-based variances. So my view again, the Fay-Harriott or any other model with random effects can be used for selecting an appropriate predictor. but the prediction mean square error should condition on the actual small area parameter of interest. If accepted, the only random process that should be accounted for is the design-based prediction mean square error over all possible sample selections. I'll just say the last two lines. It's a formidable challenge how to actually estimate what I call the design-based prediction mean square error. But I know other people are working on it, and I myself am working on it. I want to just touch as the dessert, no more equations, about this last question. Are universities preparing students to work at national statistical offices? So my starting point is that the importance of national statistical offices in modern society is not in doubt. I should also say that national statistical offices are among the largest employers of statisticians and economists. So I want to answer this question. What I did is to consider three central topics in the work of national statistical offices: survey sampling, seasonal adjustment and trend estimation, and national accounts. What I did is to browse the curriculum of undergraduate and graduate courses in statistics and economics at the top 25 universities in the world, as they are ranked by the Shanghai Academic Ranking of World Universities. And here are my results. Only 11 universities out of the 25 offer a course in survey sampling. All universities offer a course, or more than one course, on time series analysis and forecasting. But there are no specialized courses on seasonal adjustment and trend estimation. And I don't have to tell you that seasonal adjustment and trend estimation is a very major component in the work of National Statistical Office. Sometimes we only publish seasonally adjusted data. And actually, I found only 3 time series courses for which seasonality is even mentioned in the curriculum. There are no specialized courses on national accounts. And again, I don't have to tell you how important national account is in every country. At best, national account is mentioned occasionally in macroeconomic courses, mostly with reference to the GDP. So, here are just a few remarks, and I finish. One can ask, what is actually the role of universities? Are they supposed to train students to work at workplaces? Should university focus solely on research and educate new generations of researchers? I think this was the old philosophy. Without going into this question, I should say that the 3 topics that I just mentioned and many other topics underlying the work of national statistical offices require advanced theory, no less than in other courses that we teach regularly. Teaching courses on these topics is in no conflict with the view that universities should concentrate on research. It can be argued that the reason for the lack of courses related to the production of official statistics is the lack of expert researchers to teach them. But this is exactly the problem. Students are not exposed to these 2 topics during their studies, and hence they don't even consider them for their academic research. Now, I know that statistics has changed dramatically in the last decade. Survey sampling, time series analysis, and other courses should change and adapt accordingly. Here are some good news to finish. There are several universities around the world that do emphasize survey sampling in their teaching and research. There are several university master programs in official statistics. Many of you may be familiar with the JPSM in the United States, the MOFSTAT in the UK. The European Union has recently established a European Master Program in Official Statistics. So there seems to be a growing recognition of the importance of production of official statistics by academic institutions. So my last comment is that NSO should strengthen the ties with the academia by helping establishing specialized courses on production of official statistics and involving more academic researchers in their work. Thank you very much.